Hello everyone, this is Professor Roman. Welcome to the 40th video in my video lecture series, An Introduction to Discrete Mathematics. Let's take a look at our final application of Catalan words and Catalan numbers, and this is to permutations. There is a rather vast subject in combinatorics called pattern avoiding permutations. And it is, in fact, currently the subject of much research because there's a lot we don't know about this. But that's not going to be a problem for us. We're going to deal with some simple applications. So I need to begin with a couple of definitions. Let Sn denote the set of all permutations of Zn. And suppose pi is such a permutation. A subsequence of pi of length k is a permutation obtained just by selecting k, not necessarily consecutive, elements from pi. So for example, this permutation 1, 2, 6, 4, 5, 3, if I pull out 2, 4, and 3, I will get this subsequence. The order of the elements in the subsequence is the same as it is in the original permutation, and that's important. Also, a pattern of length k is a permutation of the set zk whose entries are meant only to indicate relative magnitude, and relative is the key word here. So for example, the pattern 3, 1, 2 simply means an integer followed by a smaller integer, because 1 is smaller than 3, followed by an integer in between the first two, because 2 lies between 3 and 1. This pattern, 1, 2, 3, 4, 5, simply means an increasing sequence of 5 integers, any 5 integers. So the numbers in the pattern have no meaning, intrinsic meaning, no meaning per se. 3 doesn't mean 3, it only means something bigger than 2 and smaller than 4. One could describe this in words by saying an integer followed by a small integer followed by an integer in between, as I have done. But what happens when the pattern has 10 integers in it? And you're not going to be able to come up with a sentence that's going to, make any sense. So that's the reason we use the digits in order to express relative magnitude. If B1 through Bk is a pattern of length k, then a permutation pi in Sn is this pattern B1 through Bk avoiding if it contains no subsequence with this pattern. So the pattern doesn't have to appear in consecutive elements of the permutation. It can appear anywhere. So example, this permutation 1, 5, 6, 7, 3, 2, 4, if you look at the 7, the 3, and the 4, you will find an integer followed by a smaller integer followed by an integer in between. And so this permutation is not 3, 1, 2 avoiding, because the 7, 3, 4 fits the pattern 3, 1, 2. This permutation actually is 3, 1, 2 avoiding, and I will invite you to show that, to prove that. It takes a little doing. I mean, it's not difficult, but it's a bit time-consuming. You have to justify that there is no pattern of this form 3, 1, 2 anywhere in this permutation. Now, as I mentioned, the subject of counting pattern avoiding permutations is quite complex. But we're going to confine ourselves to 3-digit patterns, and we are almost going to count all of them. And you'll have to wait till the end when I explain the word almost. Okay. Now, one approach to understanding these permutations, pattern avoiding permutations, is to borrow some topics from computer science, some data structures. So let's look at those now. You may be familiar with this if you've had a class in computer science. A stack is a data structure that stores objects in a linear array, so they're in a line, but for which insertions and removals occur only at one end of the array, which is known as the top of the stack, because usually stacks are visualized as a vertical column of objects where you can access the objects only at the top. In fact, the prototypical example of a stack is a stack of dinner plates. And so a new plate can only be placed on the top, and if you want to remove a plate, you must remove it from the top. That's a really good image for a stack. So instead of plates, it could be numbers, it could be other mathematical objects. Adding an object to the top of a stack is referred to as pushing the object onto the stack, and that's a push operation. Removing an object from the top is called popping the object off the stack, and that's a pop operation. On the other hand, a queue, and we'll look at the spelling, Q-U-E-U-E, is a data structure that stores objects, again, in a linear array, in a line, but for which insertion is done at the end of the queue and removal is done at the beginning of the queue. And the prototypical example of that is the long, long lines at the bank. The front of the queue, or the beginning of the queue, is the next person to the teller, next person to be, waited on by the teller. And when you want to join the queue, you join at the back or at the end of the queue, unfortunately. Now let's consider a game that has an input queue, which is over here, and it has an output queue over here, and it has a stack in between. So we're looking at the left-hand portion of this image for now. The beginning of the queues are on the left here, A1 and B1. The end of the queues are on the right. Okay. On the right side in this figure is the initial state of the game. So the input queue is full, but the output queue is empty and the stack is empty. And we say that the input queue here contains the input permutation. So that'll be B1 through Bn in this figure. Now at any stage in the game, we can do one of two things. And that's illustrated here. Here again is the input queue. The beginning is over here. The end is on the right. Same thing for the output queue. We can do a push operation. So we take the next item on the input queue and we pop it onto, we push it onto the stack. Okay. The reason it's called a push is if you think about the dinner plate analogy, you have all these dinner plates in the kitchen of a restaurant, and there's generally a spring-loaded tray at the bottom, so it will keep the stacks at the top. It'll keep the dishes at the top of the stack, so you can grab the next one. When you pull a dish off, all the remaining stacks move up one. So to put one on, you have to push down on the existing plates in order to add the next plate. Okay. You can also do a pop operation. You can pop the top of the stack onto the end of the output queue. It takes a little while to get used to the terms input and output queue and push and pop, so just hang in there. I'm going to refer to a sequence of pushes and pops that results in the entire input queue being moved to the output queue. So the input queue is then empty, the stack is empty. As a legal procedure, that's just a term I made up for this discussion. Now, in general, there are many legal procedures. The only thing they have in common is that they have to have exactly n pushes and exactly n pops so that everything gets moved to the output queue. Once a legal procedure is finished, the permutation in the output queue is called the output permutation. So let's do an example. I have 3 columns here, the output, and this is the output queue, the stack, and the input queue. So this is the initial state. 1, 2, 3, 4 is the input permutation, and the stack and output queue are empty. First operation is a push. There's no other choice at this point. You can't pop anything off an empty stack. So it's not a hot air popper. Sorry. So we push 1 onto the stack. It takes it off the input queue. Then I did another push. Now 2 is on the stack on top of 1. Then I pop a 1. Then I pop the top of the stack, the 2, onto the output queue, and that reduces the stack, doesn't change the input. Another pop will move 1 onto the output. Now notice already that 2 and 1 are in a different order than they were in the input. So this process scrambles the input permutation, generally speaking. Another push operation will move the 3 onto the stack, leaving only 4 in the input queue. A pop will put the 3 on the output queue. At this point, we have no choice but to do a push. I keep saying that, I'm sorry. To do a pop. No, that's not right. I did the push onto the stack here. Now I'm doing a pop of the 3 onto the output. Then I can do a push and move the 4 into the stack, push it on the stack, and now I have no choice but to pop the final element of the stack onto the output. So the output is 2, 1, 3, 4. Well, how does all this relate to Catalan words? Well, we can denote a push operation by U and a pop operation by O. Then a legal procedure can be described by a word W over the alphabet UO. But not all words correspond to legal procedures. In the first place, a legal procedure has to start with a push. So it has to start with U. The word has to start with U. Since the stack is initially empty, you can't do a pop operation. Also, at any stage, the number of pops cannot exceed the number of pushes. If you only pushed 5 elements onto the stack, you can't have popped 6 elements off of the stack. So the number of U's at any stage, in other words, for any prefix of W, must be bigger than or equal to the number of O's. And finally, at the end, the number of pops must equal the number of pushes, so everything is on the output queue. What do you think? A legal procedure is just a Catalan word of length 2n over this alphabet UO. Conversely, any Catalan word W over this alphabet UO of length 2n will describe a legal procedure. And to see that, we have to dig down into the process here. The first letter in W is a U because it's a Catalan word. It's weakly U dominant. So we can certainly perform that push operation, push it onto the stack. So suppose we have performed the first K operations specified by this prefix. The issue becomes whether or not we can perform the next operation, the K plus first stack operation, push or pop. If we can do that, since K is not specified here, we can do the entire word and get a legal procedure. Well, there are only 2 ways in which this might not be possible, that we can't do the K plus first operation. The first possibility is that the next operation might be a pop, but the stack is empty, so there's nothing to pop. But if that's the case, if the stack is empty, it means we've performed an equal number of pushes and pops up to that point. In other words, through the kth operation, the kth position in the word, which means we have a tie in that word at position K. Well, because the word is U dominant, the next operation has to be a U, a push. So this possibility that we're trying to do a pop when the stack is empty cannot occur. The only other way that this operation can fail, the K plus first operation, is if it's a push onto the stack, but the input queue is empty. But if the input queue is empty, we've already performed n pushes to clear the input queue. Therefore, all the remaining operations have to be pops. So we can't be in a situation where the next operation is a push when the input queue is empty. So the only way we cannot perform the K plus first stack operation is covered by these 2, but these 2 can't happen. So we know we can continue to perform the operations specified by the Catalan word W, which means W is a legal procedure. So, theorem. In the game described above, the legal procedures are precisely the Catalan words in Cn of UO. And so there are Cn possible output permutations for any given input permutation of length n. We've counted the number of possible outputs. Well, we haven't yet tied this into this business of pattern avoiding permutations. So let's continue. Suppose the input permutation is just 1 through n in order. This isn't any loss of generality because we can always arrange it this way by relabeling the input before we start. We can undo that relabeling when we get to the output permutation just by reversing the labeling. But when the input permutation is 1 through n, the output permutation is called a stack permutation. And there's a couple of things to note about this situation. It's because the input permutation is the numbers 1 through n in order. The integers on the stack at any time are in increasing order from bottom to top. Higher up in the stack are the bigger numbers. And it would be useful for you to think on that and make sure that makes sense to you. The integers in the input queue are larger than the integers in the stack or the output queue. The biggest numbers are still on the input queue. Now we can show that a stack permutation, which I'll call sigma, is 3, 1, 2 avoiding. And here's how we see that. Suppose that sigma contains the pattern 3, 1. So sigma would look like this. Some stuff here, C, more stuff, A, more stuff, potentially, where C is bigger than A. That's the 3, 1 pattern. Integer followed by smaller integer. Now at the moment that A is popped off the stack, remember this is the output permutation. The moment that A is popped off the stack, everything else on the stack is smaller than A because the elements increase in order as you go higher in the stack, so the top element is the biggest one. What about the elements on the input queue? They're larger than anything else, which means they're larger than C. So the elements on the stack are smaller than A, the elements on the input queue are larger than C, so there are no integers between A and C available to add to the output permutation. If you take the element off the stack, it's smaller than A, so it's not in between. If you push an element off from the input queue to the stack and then pop, it's bigger than C. So we're either going to be bigger than C or smaller than A. We're not going to be in between. So sigma cannot have a 3, 1, 2 pattern. It's going to be a little more work to prove the converse, that any 3, 1, 2 avoiding permutation is a stack permutation. Well, from the initial configuration of the game, we can place A1, that's the first element in sigma, to be first on the output queue. All we have to do is start pushing elements, integers, from the input queue onto the stack until A1 appears at the top of the stack. So if A1 is buried 5 places in the input queue, 1 through n, we just pop off the first 5 integers, A1 is now at the top of the stack. We can pop it off the stack and put it in the output queue. It'll be the first element of the output queue. So suppose that we have just popped AK onto the output queue, and that up to that point we have A1 through AK on the output queue. So it looks like this. So far so good, A1 through AK, some stuff on the stack, the rest of the input queue. And again, this SU is the biggest element of the stack, okay, smaller than all the A's, smaller than AK in particular, and these are all the biggest elements anywhere. So we have this order on the stack, S1 through SU, and AK is bigger than SU because we just popped it off. So it was at the top of the stack. It was the biggest element on the stack. We need to show that we can get AK plus 1 onto the output queue right next to AK. So AK plus 1 would be the next pop off the stack. Well, the issue is, where is AK plus 1? If AK plus 1 is buried on the stack, that is not going to happen. So let's take a look at the possibilities. If AK plus 1 is on the top of the stack, if it's SU, then of course we just do a pop and we're done. If AK plus 1 is in the input queue, that's not a problem because we can always we can always push onto the stack everything in front of AK plus 1, then push AK plus 1 onto the stack and immediately pop it off. It'll follow AK. The only other problem is AK plus 1 could be, as I said before, in the stack below SU. But that can't happen because then AK plus 1 would be less than SU, and SU is less than AK. Now SU is not any of A1 through AK. It's still on the stack, and it's not AK plus 1 because we're assuming it's buried below SU. So when we look at sigma, we see it's A1 through AK plus 1, some other stuff, SU, and that has the forbidden 3-1-2 pattern. So this case is not possible because we're assuming that sigma is 3-1-2 avoiding. So we have shown that AK plus 1 can be placed immediately following AK in the output queue, and so sigma is a stack permutation. So here's our theorem. A permutation is a stack permutation if and only if it is 3-1-2 avoiding. The Catalan number Cn counts the number of 3-1-2 avoiding permutations of size n. It's worth noting that this theorem can be very helpful in showing that a permutation is 3-1-2 avoiding, rather than having to pick the permutation apart to search for a 3-1-2 pattern and hoping you can convince someone else or yourself that there is no such pattern. You can use this stack game. So remember this permutation I mentioned earlier. I said it was 312 avoiding, although it may take a while to sort that out. Well, what you can do is start the game at the end. So put this permutation on the output queue. The stack and the input queue are empty. And do a sequence of reverse operations. Move from the output queue, push onto the stack, or pop from the stack onto to the input queue. If you can do that in such a way that at the end the input queue is 1, 2, 3, 4, 5, 6, 7 in order, then you have shown in effect that you could have started with 1 through 7 on the input queue and eventually come that the output permutation would be sigma, and so the theorem tells us that sigma is 312 avoiding. That's not very difficult. I'm going to leave that for you to try. And drawing some pictures is going to be very helpful. Draw the kind of pictures that this kind of thing here, but for the reverse direction. Now we're almost done, but not quite. What about other 3-digit patterns? Well, we can make some good progress, but we need a couple more definitions. The reverse, and I wrote that as pi super r, of a permutation pi is the permutation formed by reversing the order of the integers. So 14253 becomes 35241. Just read the permutation backwards. 35241. And the reverse operation is clearly a bijection. The complement of a permutation pi in Sn is the permutation pi prime formed by replacing each integer k by n plus 1 minus k. So k equals 1, 1 gets replaced by n, 2 by n minus 1. When you get all the way down to n, or so I'd say all the way up to n, it's replaced by 1. So there's a reversal in size. So 14253 becomes 52413, and I'll let you get the details on that. This is also a bijection. It's reversible. Why introduce these definitions? Well, here are some facts that I'm going to let you prove. A permutation pi in Sn is 312 avoiding if and only if its reverse is 213 avoiding. Pi is 312 avoiding if and only if its complement is 132 avoiding. And pi is 312 avoiding if and only if its reverse complement is 231 avoiding. So I'm going to let you sort that out if you are interested. But the point is, the bijections imply that the Catalan number Cn counts the sizes of each of the following sets: the 312 avoiding permutations, the 213 avoiding permutations, the 132 avoiding permutations, and the 231 avoiding permutations. So we got a lot more for our money here than just 312 avoiding. Finally, there are still two other 3-digit patterns, 123 and 321. But the details for these patterns are a little more involved. And I've decided it's just too much to go into. But nonetheless, it is still true that the Catalan numbers will count the number of avoiding permutations for those two patterns as well. So the Catalan number Cn counts the number of A, B, C avoiding permutations of Zn for any 3-digit pattern. Okay, we are done. If you've hung in this far, I compliment you. This was not easy going. It's going to get easier now. So when we start chapter 8. Thank you for watching, and I hope to see you in the next video.